In the last lecture, we have discussed few problems related to a particle in one D infinite potential well or in a particle in a box. Now we consider few other involved problems. Consider a semi-infinite potential well as shown in this figure. The potential at x is equal to 0 shoots up to infinity, while it remains 0 from 0 up to a, and then it is v0. So the potential in this case is equal to plus infinity for x less than 0. It is 0 for x less than a greater than 0, and it is v0 for x greater than a. So this is the semi-infinite potential well. We have a particle of m, mass m, situated within the well with energy E less than 0, E less than v0. What is the bound state energies? Now we differentiate three regions as this. So this is the region 1, this is region 2, and this is region 3. Since the particle cannot go to the left of the origin, phi 1 is 0. In this region, the wave function is that of a free particle, and since there is a possibility that the particle moves back and forth, so we take it, assume its solution in the form of a stationary waves, a sin kx plus b cos kx with k square is equal to twice m e by h line square. And for region 3 we write c e to the power minus rho x with rho square is equal to twice m v0 minus e upon h line square. Since v0 is greater than e, rho is a real quantity. First boundary condition is that phi 2, the boundary condition is that phi 2 at x is equal to 0 has to be 0. This clearly indicates that b is equal to 0. So this part goes. Now the simplified form is this. Second boundary condition is phi 2 at a is equal to phi 3 at a. This gives you a sin ka is equal to c e to the power minus rho a. And third bound, phi 2 prime at a is equal to phi 3 prime at a. You see that we cannot use the continuity condition of phi prime at x is equal to a, because there is an impulsive force acting over there. So it is Ka cos Ka is equal to minus rho c e to the power minus rho a. If we divide these two, we get cot Ka is equal to minus rho by k, as we have done in the case of finite potential well. We write it as cot u is equal to minus u upon um square by u square under root, where u is equal to Ka and um is equal to twice m v0 times a by h cross. It's the strength of the potential, and the solution was obtained as in this is the this is pi, this is 2 pi, and this part is goes to minus infinity as u goes to 0 and approaches 0 from the left hand side as u tends to um. So we must write line. This is the line. So this is the nature of the graph. You say this is pi by 2. This part is pi by 2. So if the strength of the potential be such that is less than pi by 2, there is no bound state. The bound state will be only there if is greater than pi by 2. So we see that if less than pi by 2, no bound state. And if is between pi by 2 to 3 pi by 2, there is no more bound state. Only bound state will be there when is greater than 3 pi by 2. So we write that if is less than 3 pi by 2 and greater than pi by 2, one bound state. Then if is pi two bound states. Because the upper half, there will be no bound state from the upper half. So the bound state only comes from the, so to say, odd parity states. This is one problem. And you can find out the UG, this is U1, this is U3, and so on and so forth. You can find this out by computer programming. Now there is a question generally asked like this. We have two potentials. This is the energy, and we have another potential. This is 0 minus a by 2 plus a by 2, v is equal to 0, v is equal to v0. This is v goes to infinity, v is equal to 0, a, x-axis, this is v0. This is the situation. Which one, the question is that which one will definitely support a bound state and which may not even support a bound state. We know that in this case the solution has two parts. This even part is like this, and even if comes there, there is an intersection of even with the cot function in between 0 to pi by 2, so it definitely gives a bound state, at least one bound state, however shallow the well may be. But in this case there will be a bound state only this condition is satisfied. If happens to be less than pi by 2, there is no bound state. And then the last problem of the category, in the 9th lecture we have considered a particle is moving in one dimension under the action of an attractive inverse potential. A problem is related to the same thing is this. Let me write the problem. For a 1D particle, with energy. Energy is given by minus h line square alpha square by 2m, the bound state energy, and the wave function is given by zero. This is find V. This is the problem. So we write first time independent Schrodinger equation. Time independent Schrodinger equation. This is minus h line square by twice m psi double prime of x plus Vx of x psi of x psi of x for x greater than 0. So psi prime s and psi double prime is minus alpha. If we allow or use all these things in this equation, alpha square x minus 2 alpha n and alpha n and e to the power minus alpha x are present in every one, so we ignore that, and this is minus h line square alpha square by 2mx. Then this term is plus h line square alpha by so we have phi of x is equal to minus h line square alpha by x for x greater than 0, and this is plus infinity for x less than 0, as the particle cannot penetrate to the left of the origin. That's all. From the next class onwards, we shall start a harmonic oscillator, which is indeed a one-dimensional problem. But since the system is very special, so we will not continue this heading the Schrodinger equation in 1D. Rather, we shall start harmonic oscillator under the heading harmonic oscillator itself.